Okay, so you can see that it's complicated, right? So, but it is, if you somehow were able to do Gauss's method with these letters and do all this stuff, pulling it out, once you got it to like you would still do, you could just do, minus D over A plus this, then minus H H over A rho 1 plus this to make these 0. Then these would be all horrendous results, and you somehow be able to like factor stuff out, or somehow, if you kept track of everything, you could get this formula by the same way that we got this formula up here. But that's not so important. The important point is that we can do determinants just by doing Gauss's method. And the crucial thing is that there's two things that although the formulas look complicated, the idea is that it's the area of the parallelogram or parallelepiped, and if that area goes to 0, then they're linearly dependent and the determinant's 0. But if it's not 0, they're linearly independent, and they enclose natural area, which is not 0. Now, let me show you. So this is what you want to do. If I have two vectors here, how do I form? Well, what you do is they can be different positions. You want to start from one. You can see that one of these vectors will rotate counterclockwise into the other. So if you take the one that you're rotating you take this and you form what you want is the determinant of X, Y, and RS. Okay? What happens is that if you did it the other way, if you flip them, you get minus the area. So what's happening is this. If I take a surface like this, I can sort of think of it as having two sides, either pointing up or pointing down. So if I flip these vectors, if I sort of imagine taking the plane and flipping it over, that's going to flip this upward arrow into this one here. So that exchanging the vectors corresponds to moving the area that points up into an area that points down. And the plus sign, this is sort of the plus side of the surface, is the minus side. So if you want a positive area, then you want to choose going this counterclockwise direction. And this is the same way as if you were choosing you want to choose, anyway, I'll leave it at that. Okay, so that's basically the story on determinants. And there's lots of other, for example, it turns out that you can see that if a matrix has, so what does that mean? What does that mean for if I have a matrix and I go to echelon form and I have a free variable? They're always determinants of square matrices. So if I have a free variable, I'm going to have a 0 row, right? Because only 2 of the 3 variables are going to be leading. That means that if I have a free variable, the determinant of that coefficient matrix is 0. Okay, so if I take some matrix and it reduces to echelon form, it has a 0 row, the determinant equals 0. When does that corresponds to there being a free variable, right? That means there's an infinite number of solutions, which means that this matrix is singular and has no inverse. Okay? So this determinant thing determines lots of things. If it's not 0, okay, if the determinant is not 0, then it has no free variables. All its variables are leading. It's going to have one solution. It's going to be the associate. It's going to be the matrix of a linear system has exactly one solution, it will be non-singular and it will have an inverse, all the opposite of these properties. So if you take a matrix and take the determinant, you know lots of stuff about it, not just that it has that it has an inverse or not. Anyway, so it's a useful function, and if you ask for what are functions from matrices to numbers that behave nicely with row operations, there's only one solution, which is this parallelepiped solution. Okay, so I think that tells this story. The chapter here actually has these formulas, for the 3x3 formula and for the other, and it has a different motivation. It says, we want the determinant to be a function that behaves nicely with row operations, and you see that it agrees with the known formulas. And so it comes through and gives you, what can we do? We can find determinants, and here's the definition. A number determines a map such that it behaves nicely with row operations, with scaling, and the determinant's one, and that it turns out that if you swap the rows, then you get a -1. Okay, so you can show from this, a matrix with two identical rows has a determinant of 0. Why is that? Well, if I took -1 row plus the other one, that would produce a 0 row. And the 0 row would give you the 0 determinant. So if two rows are identical, the determinant is 0. A matrix with a 0 row has a determinant of 0. A matrix is non-singular if and only if its determinant is non-zero. So think of, what does it mean by non-singular? It means it's the matrix of a linear system with exactly one solution. If it's square, has exactly one solution, all its variables are leading. If all its variables are leading, that it's going to turn out that when I get to echelon form, the diagonal matrix is going to have entries that are not 0 on it. I'm not going to have a 0 row, so all of the diagonal entries won't be 0, and I'm going to be able I can show that it's going to turn out that the determinant of an echelon form matrix must be the product of its long diagonal entries. There's a number of extra things that can be proved, but for example, let's look at A, B, C. This has to equal, I can pull out an A, a B, and a C. This is going to be A times B times C times 1, 0, 0, 0, 1, 0, 0, 0, 1, which equals A, B, C. So a diagonal matrix is going to have the determinant of the product of diagonal entries. Oh, also, let's say that I have an upper triangular matrix, like say A, B, C, D, E, F, 0, 0, 0, like this. Okay, but by row operations, I can multiply C by something to get rid of E and F. And once I've done that, I can multiply this row by something to get rid of the D. So but that won't change the determinant, but it'll have just A, B, and C. So this is going to equal A, B, and C. So the determinant of an upper triangular matrix, where I sort of along this long diagonal here, it has entries, and as long as this is these entries don't count once I get it to echelon form. So once I get it to echelon form, I don't need to get it to reduced echelon form. I just need to then read off the entries there. So that's also simplifies a little bit the calculation of determinants. And if the determinant is 0, what that means is that you're going to have a 0, somewhere you're going to have a 0 row, which means you're going to have a free variable in the matrix. which means it's going to be singular, which is the opposite. It's sort of like if a determinant is zero, then the matrix is singular. And that is going to be the same thing as this result here. Okay, so those were some nice results. And the rest of the chapter, apart from this procedure, is a proof that the thing is unique. So, and also there's lots of theoretical things you can do with determinants, since this chapter does a bunch of them, but we're sort of going to ignore that. So we're not going to go over all you have to sort of expand it in a certain way so it behaves nicely with permutations, and you can use that expression to prove that it's unique, and then to show that expansion, then you can get all the properties from it. So there is a lot of machinery behind these results here that says what you can do. And so I'm going to sort of ignore all the rest of the stuff in this chapter, except for the piece at the end that not determinants exist, like it's a long proof, so to speak, that they're unique. But that is good. Consequences. Oh, yeah. You can look at the elementary matrices. All the elementary matrices have inverses. They're determined. You can figure out their determinants, and then that also there's also some results you can get. For example, that if I want to know here's the formula, right? The determinant of A times B this is a matrix product is equal to the product of the determinants. And the way that works is it's sort of like what you can say is, well, it divides the case into singular and non-singular, and then uses row operations so that if it's non-singular, I can reduce the matrix with row operations to the identity, and then because I know how I can express the matrix as a series of row operations, and I know how all the elementary matrices determinants behave. So I can factor them out, and then you can do the whole thing with this. So the point is that the determinant of a product is the product of the determinants, which is important. Okay, there's another nice property, which you prove the same way with elementary matrices, that the determinant of a transpose is equal to the determinant of the original matrix. Okay. And I think, yes, here's this property here leads to the following nice situation. The determinant of A times the determinant of A inverse equals the determinant of A times the determinant of A inverse, right? But then the determinant of A times A inverse is the identity, so this equals 1, right? Because A times A inverse is the identity matrix, the determinant of the identity matrix is just the number 1, so therefore 1 equals the determinant of A times the determinant of A inverse. So if a matrix has an inverse, then the determinant of the inverse matrix equals 1 over the determinant of the original matrix. So that's sort of nice, right? So you get all these sort of general results that are nice. And then the geometry of determinants, which we've already started with, which is gone over at the end. Okay, and then we're not going to worry about volume changing maps. You can worry about how. Okay, so let us see about practice doing some problems with these.